Okay, so my name is Dragan Djuric, and welcome to Clojure is not afraid of the GPU. And just let me start with a few details about me. I am a professor of software engineering at University of Belgrade, and surprisingly, I actually love doing programming. So I've been doing this, I've been using Clojure as my primary programming language since 2009. And I also managed to put it into the curriculum at university, so I teach it since 2010. And you can find my contacts on GitHub, and the projects that I will be talking about today could be the documentation could be found at uncomplicated.org. And a few things. The slides for this talk are at dragan.rocks because .com was taken, so this was available. So I opened a new blog, and the slides are there. Everything that I will be talking about today is on the slide, so please relax and enjoy the talk. You don't have to read every word on the slides. So let's start a bit. So I've seen that Rich Hickey has a hammock, and I also have a hammock. This is my hammock. Now, I guess in Stephen King's guide about Java, these four would be some four main villains or so. Now, you remember the first time that you saw Lisp many years ago, I suppose, and there were those Lisp guys talking about their language Lisp and how it's awesome, and when you looked at it, it was like, oh, it's weird. But now, when you accommodated yourself to those parentheses, now it's the most natural thing in the world, I guess. And also, I remember the first time I saw Emacs, it was like barren, no features, ugly. I mean, no features before you learn it. Once you learn it, like Emacs is the best software tool in the world. So, today I hope to convince you that native libraries and GPUs, like graphical processing units, are also conquerable and could be used in a really nice way and efficiently. So Clojure is great, and I hope I don't have to convince you about that, so we'll skip this slide. But is it really great at number crunching? Well, I mean, it's certainly not bad. I mean, JVM and Clojure are not bad at number crunching, but I don't think that they are great either. One of my goals with these projects is to help make Clojure great for number crunching and numerical heavy algorithms. Now, what about other managed platforms like R or Python? Well, they have many uses in machine learning, in other similar numerical demanding applications. But I don't think that they are good either at number crunching. I think they're even worse than JVM. But the thing is, they integrate lots of native libraries and they get the speed. So that's a good thing. But if you need to implement your own algorithms in these languages, you have to go deeper into C, into some optimized compiler-specific code, and it's not easy at all. So the CPU itself is not so great at number crunching because it has many features, but because it has many features, it's expensive And you cannot put lots of those transistors on the chip because lots of transistors for lots of functionalities. And it's also runs pretty hot. So which brings us to GPUs. And the GPUs contain lots of simple, very simple computing units. And these computing units have a few features, not very much, not very many. But those features that they do provide are exactly those features that we lack in Clojure and JVM, like efficient floating point operations or hardware support for massive parallelism. And also they become faster and cheaper each year, so that's a good thing also. But the bad thing about GPUs is that they are notoriously hard to program. Like the development environments and tools are from the Stone Age, especially if you develop Clojure every day. Now, I will present some libraries that are part of Uncomplicate. And now Uncomplicate is a family of open source libraries for Clojure, for scientific and high performance computing. My main goal when starting with this was to create a state-of-the-art Bayesian data analysis and machine learning infrastructure. And for that to work, I also had to create some lower level libraries because what was available at the JVM at the time was really not comparable to what is available elsewhere. So the first of those libraries is ClojureCL, which is a Clojure library that enables you to take full control of Opencl and GPUs and accelerators with minimal overhead. So it's really efficient and enjoyable to program. Neanderthal is a library for high performance vectorized and matrix computations that is built on top of battle-tested native libraries in this area, and also comes with some latest GPU libraries. Bayadera goes even beyond that and aims to be much better and faster than other tools from this area. So let's start with some code. Dot product is one of the simplest vectorized operations that you use in matrix computations. And to make it less abstract, let's say that X is a vector of some quantity of some product, and Y is a vector of unit prices of those products. So if you want to know the total amount in dollars, we just do the dot product. And on the diagram, you can see how it's computed. And it's computed by multiplying each pair of X and Y's and then summing everything up. And this is quite simple operation. It scales linearly. It requires 2n floating point operations and 2n memory reads. And accessing memory is really one of the most important things when optimizing such algorithms, even more important than floating point operations. So it's simple and easy, and in fact it's so easy that in Clojure it's a one-liner, like you map with multiplication over x's and y's and then reduce with the plus operation. And it actually, how fast is it? Well, it looks pretty fast to me. For 100,000 of those elements is 14 milliseconds, which is not bad. But the point is that we never need dot product itself. We usually need it as a part of some larger algorithm. So these 14 milliseconds quickly add up. Naturally, we seek for a faster solution. We get the idea that in Clojure we can optimize it by using loop recur. And can it help? Well, yes, but not that much, because not even an order of magnitude faster. So, as a side note, using a library like Fluokitten can give us top speed for the data structure at hand, while also giving us a high level of abstraction and compact code, but not much not faster at all than loop recur. When it comes to numerical algorithms, and we have lots of data and we need speed, it always pays off to turn to primitives. So in Clojure that means Java arrays, primitive Java arrays. So in this case, for the same example, 76 microseconds, which is like 30 times faster than loop recur and 200 times faster than the idiomatic Clojure. But we pay the price with uglier code and mutability. And what can we expect from some optimized native library in this case? As you can see, Neanderthal can give us simple operations, simple API that we can use for those kinds of operations. And it's even faster than primitive Java, like 32 microseconds for this example, but only a couple of times faster. Well, I mean, isn't that pathetic? Like, who would bother with learning new stuff and using a library for that? Like, well, be patient, please. So let's try Neanderthal support for GPUs. I've heard that Google and Facebook are like getting some incredible results with GPUs and accelerators in deep learning or so. So we think, okay, we will also use GPUs and get those incredible speeds. So a good thing about Neanderthal is that it also its API supports pluggable engines, and it already comes with a native engine optimized and also GPU engine. So the API still stays the same, as you can see. We just use some ClojureCL to choose the GPU, the device, and set up the device that we are going to use. But in this case, well, 327 microseconds. Well, this is certainly not a bad result. I mean, it's still much, much faster than idiomatic Clojure or the loop recur, but it's 4 times slower than primitive Java arrays and 10 times slower than Neanderthal CPU engines. So what is wrong here? Well, remember the movie Forrest Gump? I mean, when you use a huge boat to catch a few shrimps, well, it certainly doesn't pay off. I mean, if you want to do shrimping for a living, then you better catch millions of those things. And if you don't need millions, if you only need a handful, well, then go to the fish market, don't use the boat. So when trying to speed up your algorithms, you have to take care of at least a few things. The first is that your algorithm have to be suitable for parallel computation and for GPUs. And luckily, the way we program GPUs and the way we program in Clojure, like functional programming with MapReduce or so, are quite similar. So the map operation is embarrassingly parallelizable. So if you have lots of mapping, it will be incredibly fast. Reduce is tricky on massive parallel devices and tricky to program. So ClojureCL luckily comes with a toolbox that can help even with that, but you have to consider it. Also, you have to have lots of data and computation. So because there are some communicating overhead with GPU, so if you don't have large tasks, well. And also, programming parallel devices is not a totally easy task. Now, a typical example of a computationally expensive algorithm is matrix multiplication. So if we have two matrices, A and B, and we multiply them, we get the third matrix C, and each element of C is actually a dot product of a row of A and column of B. So the complexity of this algorithm is cubic, and it requires a lot of floating point operation, but what is even more challenging is that it requires a really complex reading and writing patterns from memory, because memory is linear and matrices are not one-dimensional. So it's not it's trivial in a naive way, but it's really difficult to optimize efficiently. And the Clojure implementation seems straightforward, if not overly pretty, but straightforward. And for this small matrix, these small matrices, like 64 rows and 64 columns, let's see the speed, well, 40 milliseconds for such a relatively small task. So I'll skip trying to implement this in primitive arrays or so, because it wouldn't work well, especially if the data doesn't fit in the cache memory. So let's see Neanderthal. I mean, the API is certainly simple, because these are some standard operations, and many number crunching algorithms can be expressed through these standard linear algebra operations. So if we can express the algorithm through them, well, we should. It is much cleaner and much faster. So as you can see, the same 64 times 64 matrix problem is 1,000 times faster, like 40 microseconds versus 40 milliseconds. And here, this is only an example of one operation, of course, matrix multiplication, but it's an operation that is a good representative of how some implementation is well done. So here Neanderthal is compared with a well-optimized Java library, not some naive code, but really good performant Java library. And as you can see, for large matrices, it is of course much faster on the same hardware, on the same CPU, one thread on one core. But it is also faster for small matrices. So the urban legend that for native library to be useful, you have to have lots of data is really a myth if you do it properly. So even for small data structures, it can be faster. And finally, let's see some GPU in action. So the same problem, matrix multiplication, just with some large matrices, like 8,000 times 8,000. And Neanderthal's optimized CPU engine, 18 seconds. GPU engine on a quite old, my desktop Radeon 290X, which is 3 years old, I think. It is less than 300 milliseconds for such a large problem. So it's 60 times faster for this particular example than native CPU, and 1,200 times faster than optimized Java library. Versus idiomatic Clojure, well, who knows? And of course, there are lots of other operations that are not even delegated to the native library. You need to shuffle that data to transfer it to GPUs or other memory. So there are lots of other useful operations that Neanderthal gives you. Now, is that all? I mean, is everything you need to just use some linear algebra operations or a good performant library and your code will be like magically super fast. Well, of course not. Of course not. The point is that you get a lot of fast operations for free, and that's a good stuff. You should use it whenever you can. It can help a lot. But we all have our custom code. We all need to build some non-standard algorithms or operations. And now we come to the meat of this talk. Like, how can I program my own custom stuff and do it at these speeds? So get some really fast performance. Well, just a second. So, Opencl is a standard that enables us a unified way to program GPUs, accelerators, and also CPUs in an optimized and efficient way. It is supported on AMD hardware, on Intel hardware, on NVIDIA hardware. So actually you can program lots of different devices. The problem is it is quite complex. It uses Opencl C as a standard. So for example, this great book that I recommend for learning this stuff, it has a hello world, and this hello world is like 170 lines of code. So it's really verbose, and also NVIDIA's CUDA is not much better, or not better at all. Clojure is certainly much more pleasant to work with. I hope you agree with that. So, luckily, there is a library for that. ClojureCL is a library that enables you to take full control of your GPU while ameliorating those difficult sticky points of Opencl. So, you write your kernels, which are tiny code chunks that actually run on those small computing units on your GPU. And these chunks are written in a simple subset of standard Opencl C language, but everything else is done in Clojure. Stuff like managing platforms, devices, hardware, contexts, asynchronous command queues, loading and compiling programs, managing memory, enqueuing the actual computations to those queues. Everything is in Clojure. And ClojureCL also comes with a toolbox that has some additional functionalities that help you with some tricky stuff, with reductions, for example. And I know this is overwhelming at first, so that's why I make sure that for all these libraries, I always create lots of examples. I always pick up one good textbook or developer's book like this ClojureCL in action, and I translate most examples to Clojure code. So actually, if you want to learn this stuff, you take the textbook, you read, and you can follow it in Clojure. So I take care of the learning part, so you're not left with just some code and find your way out. There are tutorials, and there is lots of documentation on uncomplicated.org. So let's see how could we implement our own dot product on the GPU. I mean, finally, some real GPU code. And ladies and gentlemen, I present you a kernel. So see, it's nothing to be afraid of, nothing too complex. It's pretty much similar to a Clojure function that will be used in a map operation. So mapping over some array or vector. So as standard and straightforward simple C, you don't need to be an expert in C to learn this. We just need to set everything up and fire it off on the GPU. And in plain OpenCL, it would be really lots of hundreds of lines of code. In Clojure, it's not as simple as I wish it were. I mean, but it's pretty straightforward. And actually here we see a low-level ClojureCL code. So we are not using any help from Neanderthal, although we could get this simpler. So I also want to point out that this is the whole program. So this is not some snippet. This is the whole program that was used to generate this result that you see below. So the whole presentation is actually generated from Emacs, from the live code. So what do we do here? We get the context, we choose the device, in this case the best device that I have on my computer, not this one but on my desktop. Don't count on laptops if you want to do this stuff. So then we create an asynchronous command queue, we load the code that you have seen on the previous slide. We compile the program. What else we do here? We transfer the data from JVM, from Clojure data structures, from Java arrays to memory on the GPU. We enqueue the computations and we read the result. And recall that to implement dot product, we need to map, to multiply those pairs, but we also need to sum everything up. So now we need another kernel, summing kernel. And because it's reduction, it would be a bit difficult on to do on CPU, but luckily we can use some helper functions from ClojureCL toolbox. As you can see, we just added work group reduction sum. This function will reuse local memory and cache to do this in an efficient way without you having to worry about that too much. And we also improved the multiply kernel from the previous slide a bit because the data is already loaded in memory, so we do a small part reduction there to make this more efficient. But also it's nothing too complex, I hope so. And calling those reduction kernels recursively could be a challenge, but thanks to ClojureCL's helper functions like enqueueReduce, it's only a few changes to the previous code, and now we can see the total result, 47.5 down there. The code is quite straightforward, especially if you compare it to the real Opencl C code. Then you will see how this is really simple. And I achieved some great speed-ups with this approach in my work on Bayadera library. Bayadera is a highly opinionated Bayesian probabilistic Clojure library that is much faster than the state-of-the-art established environments for Bayesian computations, really. It is not as mature as they are, but it is much, much faster. How I did it? And I built it primarily for doing Bayesian data analysis, but I also plan to use it for some probabilistic machine learning, and it can be used for some higher level stuff. Really lots of useful, reusable functions are there. And I don't have to talk about Bayadera in detail, and I hope I will at some future conference, but I want to talk about its main goals. And the first and foremost goal is it's built for programmers. So lots of programmers are trying to get into machine learning or statistics or data analysis, but all the tools and environments are like geared towards statisticians and non-programming people, which is of course logical and all right. But I wanted to build something that I would enjoy using. So the first goal is that programmers should feel at home. And of course, you can do all these data explorations and model building and everything, because Clojure is pretty interactive. But the idea is that once you build these models, you can put them on server and make them efficient. And it's not meant to be like a copycat of what R or Python do, but it's actually meant to be different and better for what I needed to do. And what actually it means to be Bayesian? It means that you treat everything probabilistically. Everything is a random variable that you typically describe using some distributions. And then in probabilistic data analysis and Bayesian branch of this, we base the inference on bias rule. So basically we have some prior hypotheses, and then we have likelihood of data when the hypothesis is given, and we have an evidence, the probability of total data, and we want to compute what is the probability of some hypothesis given this data. So it's like going backwards in inference. And I know it sounds and looks like Greek to you now, but it's simple and easy once you get the maths. But the main problem that held Bayesian methods dormant for 200 years, like until 10 or 20 years ago, is that in general case it is ridiculously hard to compute. I mean ridiculously hard, even today. So as you can see in this formula with lots of integrals and some products or so, and vectors. So usually we don't have nice unimodal, one-dimensional problems that fit well into formulas and give some analytical results that we can easily compute. No. Usually we have some like multimodal, many-dimensional problems, descriptions for functions that don't fit at all. So we cannot get the analytical solution. And we have to explore this really, really complex hyperspace with some numerical simulation. So to get the answer, really, we have to compute something that is hard to compute and something that is not so hard to compute, and then do it many times, like millions or billions, and then divide it by something that is actually impossible to compute with brute force. So what we do, one of the techniques that can solve this is Markov chain Monte Carlo simulation, like MCMC. And it can simulate and draw samples from an unknown distribution. That's the thing. It can draw samples from something that you don't know what it is. But once you get many, many samples, you can approximate the actual result. And to do this, you only need to do the hard part and the acceptable part in computation, do it zillions of times, but luckily you don't have to do this impossible part. So now we have something that is not impossible to compute, but it's still hard to compute. And that's why GPUs can help. Now, the tricky part is that MCMC is practically a sequential algorithm, so it's really difficult to parallelize. So it's really not good a fit for GPUs, but luckily people found a way to parallelize even that. And I implemented that on GPUs and got really great results. I will talk about this in a few minutes, but I do not expect you to follow this code, but I'm showing it just an example of what a user should write to build a model. So this is a likelihood function that you have seen in this formula before. And it is really some straightforward C code that uses, in this case, student's t distribution that Bayadera provides in its library. And this is actually the most complex part that you would have to write. to plug it in Bayadera. And also you write the prior function describing your knowledge, which is also pretty straightforward with some statistical functions from Bayadera. We set it up in Clojure, we load the data, and run the computation. And please note that this is not a hello world example. This is an example from a real data analysis from some of the later chapters of a really good textbook doing Bayesian data analysis that I recommend you to get if you are interested in trying to learn this stuff. So this is the whole robust linear regression example. As you can see, it's some pretty straightforward Clojure code, nothing too exotic, although it's not the simplest that you saw probably. But what I really wanted to show you is this. Like Bayadera runs circles around the equivalent tools. For example, in this particular analysis that I showed to you, Bayadera took more than 60 million complex samples in 267 milliseconds, which is around 4 nanoseconds per sample. And this is 4 nanoseconds for some complex function that required lots of reading from memory, lots of writing to memory, lots of computing statistical functions, so not some trivial stuff, really lots of operations. And for example, JAX and STAN, which are C++ tools that are used, C++ engines that are used from R and Python. For the same problem, they took 20,000 samples in several minutes. So actually, if you compare sample to sample, Bayadera was like 2 million times faster taking samples. Of course, it is not a fair comparison, I have to admit, because these tools are using different kind of MCMC. But what is fair, I think, is to compare the total time for exploring this space and getting the result. And if we just compare the total time of this analysis, Bayadera was 1,000 times faster and also gave much more precise results, because when you have more samples, you can produce much finer histograms. And the question that is also interesting is this. What if we implemented this MCMC algorithm in Clojure on JVM? Because Bayadera also provides lots of Clojure statistical functions. It wouldn't be a problem. But it would be slow, I think. So I didn't bother to write this because it's not simple code. But I wrote the equivalent of those likelihood and prior functions in plain Clojure with optimized primitive Bayadera functions. So let's see some comparison that is unfair to GPU, because I created an example taking probability density evaluation of these likelihood and prior functions. So GPU is doing the actual real work with real data, lots of memory reading and writing. JVM example is just looping around with the data from cache memory. But still, GPU was 1,650 times faster for this particular function. And what about Encounter, for example? Well, it doesn't support Bayesian stuff, so no direct comparison possible. But I took something that Encounter can do, like taking 100 million samples from normal distribution, like a simple stuff. And for this example, Encounter needed 27 seconds. Bayadera, 4 milliseconds, which is 7,000 times faster. So if you ask yourself, okay, but do I need that many samples? Who needs 100 million samples? Well, if you try to do probabilistic stuff, like Bayesian machine learning or data analysis, you need many of those things. You always need many samples. Now, you may think, but who cares? I mean, 1 millisecond, 1 microsecond, 1 nanosecond. Everything is a blink of an eye. So why it's important if it's 1,000 times faster? Well, when you consider how many seconds is in an hour, or how many minutes are in a day, or such things, well, you can see that there is a difference between waiting 1 second for your computation to complete, instead of waiting 4 minutes or an hour or a couple of hours. Or you wait for 1 minute versus several days if something is 7,000 times faster. Or you have to wait 1 hour instead of a couple of months. So if you get it right, if you really get this speed up, which is not always possible, I can tell you, so don't expect it to be easy. But once you achieve this speed up, it can really be a great difference in these kinds of programming. So, that's the end. Okay, so thank you for coming here. Thank you for inviting me here. And I have to remind you that you can find the slides on dragan.rocks. You can find the documentation on these addresses for each project. Bayadera.uncomplicated.org is a future one, but others are already there, and there are lots of tutorials, and all the examples from the textbooks that I mentioned are in the test folders on GitHub in those projects. So if you're interested, please don't be afraid of this stuff. You can conquer it. And please, I don't have time to take questions here because I ran out of time. But I'll enjoy to answer everything here during the conference, or just ask questions on Twitter or forums or wherever. I will find this, or I will try my best to answer or to help you get into this stuff. So thank you for coming here and listening to me.